So our next goal is all about oxidation reduction reactions, or redox, as you might hear us refer to it when we're talking about oxidation reduction reactions. We are starting our intro with the article Flaking Away from Ferraris to Fords. It is located in your packet. There's also a SoundCloud link linked on Google Classroom that you can listen to it aloud. As you read, remember to use those close reading strategies where you note if you see something that looks important, like a definition or a key concept, or if something sparks a question that you might have. Annotate as you read so that it makes it easier to go back and find those pieces of information to refer back to them. After reading, we are going to look at some questions to check our understanding coming away from this article that really gave us a lot of information and good examples about oxidation reduction reactions, definitions, and then tying it back to the process of rust, which is something that, in terms of like a real world concept or context, it's something that we are all familiar with in some aspect. And so, question one asks us to connect the words oxidation, reduction, anode, cathode, and electrons. From the passage, if you look at paragraph 4, that passage gave you all of these definitions and tied all of these words together. The passage told us that oxidation is any reaction that involves an atom losing one or more electrons. So, oxidation is the process of losing electrons. Oxidation occurs at the anode. Reduction, the exact opposite of oxidation, reduction is a reaction that involves gaining electrons, and reduction occurs at the cathode. Oxidation and reduction are considered coupled reactions. You can't have one occur without the other. And that's because we've talked about law of conservation of mass, law of conservation of matter. Electrons also have to be conserved. So if something is losing an electron or one or more electrons, something else has to gain those electrons. And so oxidation and reduction always go hand in hand, which is why we refer to these as redox or oxidation reduction reactions. Both pieces are happening. To help you remember that oxidation occurs through losing electrons and reduction is the process of gaining electrons, you can remember the acronym OIL RIG, where it says oxidation is losing electrons, reduction is gaining electrons. Or Leo the lion says GER, losing electrons oxidation, gaining electrons reduction. How can the process of rust be sped up? The article also talked to us about this, about salt. Salt is a big contributing factor in coastal areas and then in states or areas that get frequent snow. So salt, either from the ocean or from that rock salt that we put on the roads to prevent the roads from icing, that salt dissociates and makes water a better conductor. Water on the anode surface allows those electrons to flow more easily between the anode and cathode, which speeds up that process of rust, because rust is an example of a redox reaction. In the article, the equation 2 iron solid yields 2 iron 2 plus ions plus 4 electrons is used to model the oxidation of iron metal to iron 2 ions. Explain how this equation illustrates oxidation. So we previously defined oxidation means losing electrons. Looking at this reaction, we can see that electrons are a product. Because the electrons are a product, that means they're being produced or lost from that solid iron, which fits our definition of oxidation. We are going to kind of skip over in your packet before we continue with these questions, and we're going to talk about oxidation numbers. When we're given a half reaction like this one in question 3, we can clearly see that the electrons are a product, and so electrons are being lost, telling us it's oxidation. But when we get a little bit further and we look at full reactions, we may or may not see those electrons explicitly listed. Because if it's the full reaction that's showing oxidation and reduction, we won't see those electrons physically in the equation. But we have to understand and be able to know that electrons are lost or gained by different atoms in that reaction. And so when we talk about reactions, top part of this is not necessary to know, but this middle piece is on your worksheet. It tells us that an important idea to help us recognize oxidation reactions is to identify the oxidation number or oxidation state of an atom. It's also called the apparent charge. We've talked about charges, like ionic charges, when we look at elements and ionic compounds. This is a little bit different. There's going to be some overlap because in ionic compounds, the charges that we've always talked about are the oxidation numbers. But we're going to start breaking down compounds that aren't ionic, things that are just atoms or individual ions or molecular compounds where sharing electrons, where we don't talk about them having a charge, but they have this apparent charge known as the oxidation number in that particular compound. And so oxidation numbers and charges aren't explicitly the same, but they are similar in how we talk about them and how we find them. We're going to talk through the rules for assigning oxidation numbers and then look at some examples and then some practice. So our rules for assigning oxidation numbers. If an element is in an uncombined state, so it's not in a compound, it's not with any other element, then that means that its oxidation number is just 0. Any monatomic ion, monatomic meaning one atom, so just a single element ion, that oxidation number of that ion or that element in that ion is the charge of the ion itself. Hydrogen is generally in a compound going to be a +1 charge, but in a hydride where it's with a metal, it's actually going to have a -1 charge. Oxygen typically has a -2 charge in compounds, except for with peroxides where it will be -1. In any neutral compound, the sum of all of the oxidation numbers for the atoms in that compound have to add up to 0. And then elements other than oxygen and hydrogen in a polyatomic ion, the total charges have to add up to the total charge of that polyatomic ion. So going back up to our first rule, an element in an uncombined state has an oxidation number of 0. So when I just say sodium, zinc, sulfur, chlorine gas, those are all just monatomic, not monatomic because chlorine's not, sorry. Those are all just uncombined. Those are elements in their elemental state, how they naturally exist as an element. They don't have a charge. These are all an oxidation number or oxidation state of 0. Okay, but when we have a monatomic ion, the ion specifically shows you that charge. So sodium 1 plus, that sodium has a 1 plus charge or a oxidation number of 1 plus. Zinc 2 plus, sulfur 2 minus, chlorine 1 minus. These are different than the first row of examples. If I just say sodium versus a sodium ion, those are very, very different. They're very different chemically, how they behave, how they look. Sodium, at the beginning of the year, we did that demo with the sodium that was like a very shiny, silver-looking clay-like substance. And when we put it in water, it caught on fire because of its reactivity. That was just Na by itself, oxidation number of 0. But sodium 1 plus and chlorine 1 minus are what's in your table salt. They don't catch on fire when we put them in water. They behave very, very differently. So it does matter if you're saying just sodium or sodium 1 plus. Hydrogen in compounds is typically going to be a 1 plus except in a hydride where it's a 1 minus. So in HCl, HCN, H2O, in all of these compounds, hydrogen has a +1 oxidation number. In calcium hydride, CaH2, it's with a metal, and so that hydrogen has a 1 minus charge because that calcium metal is the cation in that ionic compound. Oxygen in compounds will have a -2 charge. The only exception is peroxides, where it's O2 with a 2 minus charge. So in H2O2, if each hydrogen's a 1 plus, then we have 2 of them. That's a total of a 2 plus. It has to be neutral overall. So those 2 oxygens have to give us a total charge of -2, meaning each oxygen can only be a -1. Elements other than oxygen and hydrogen in a neutral compound have to sum total of the oxidation numbers is 0. So FeO and Fe2O3, both of these are neutral compounds. They don't show a charge, which means the total has to add to 0. For FeO, our rules tell us oxygen in a compound is -2. To make this neutral, then the iron in FeO has to be a +2. When we look at Fe2O3, again, that oxygen's a -2, but there's 3 of them. So that gives us a total -6 charge. It has to be neutral, so then we need a +6. There's 2 irons that give us a +6 charge, meaning each iron has to have a 3+ charge. So the iron in FeO and the iron in Fe2O3 have 2 different charges or 2 different oxidation numbers. 2 plus in FeO and then 3 plus in Fe2O3. So you can't just assume that they're always going to be the same. You have to solve for them. Our last rule says that with polyatomic ions, the total has to add up to the charge of the polyatomic ion. So if we look at sulfate, SO4 2 minus, we assign oxygen as 2 minus. There's 8 oxygen, so that's 8 minus. The total has to be 2 minus, so that means that sulfur has to be a 6 plus. This does not match what we would predict off the periodic table, and that's oxidation numbers aren't necessarily going to match. You're always having to mathematically solve for that last element that you're trying to find. CN 1 minus, our total has to add to 1 minus. Neither of these are hydrogen or oxygen. And so our rules tell us in a compound, do hydrogens a 1 plus, oxygens a 2 minus, except in a peroxide. And then for any other elements that are not hydrogen or oxygen, if there's more than one element left, then you're going to look at your periodic table at the elements that are closer to the outside. So closer to like group 1A or 7A or 8A. The elements closer to the outside of the periodic table, you will assign based on what we predict using the periodic table. And then you're always solving for which one is closest to the center of our periodic table. So between carbon and nitrogen, we will assign nitrogen from the periodic table as a 3 minus. The total has to be a 1 minus, so that tells us carbon has to be a 2 plus. So we solve for the carbon being a 2 plus oxidation number. We're going to practice. So for these 4 compounds, you are answering what is the oxidation number of the underlined element. These first 4 are a little bit simpler, and then we'll look at the next 4. So in barium 2 plus, this is a monatomic ion. It says barium 2 plus, so that tells us that barium has a 2 plus oxidation number. Question 2 is N2. This is nitrogen. It's diatomic, but it's in an uncombined state. It's not with any other elements. So its oxidation number is 0. It cannot be -3 from your periodic table. If this nitrogen had a -3 charge, and there's 2 of them, then we would see N2 written as N2 with a -6 charge. And it's not. It's neutral, so that nitrogen has to have an oxidation number of 0. Question 3, HI. Our rules say hydrogen in a compound has a +1 charge. So we don't have to solve for hydrogen. We assign hydrogen as a 1 plus. Question 4 is a peroxide. It's O2 with an overall 2 minus charge. So each of those oxygens has to be -1 for both of them to combine to give us -2 total. The next 4, AgBr, CuCl2, HNO3, and ClO3 1 minus. AgBr, neither of these are hydrogen or oxygen, so we're going to look at our periodic table. Bromine is closest to the outside. Based on our periodic table and predicting ionic charges, we would assign bromine a -1 charge. We then could solve if we had to answer about silver. Silver would have to be a 1 plus to make that a neutral compound. 6, CuCl2. Neither of these are hydrogen or oxygen. Chlorine is closest to the outside of the periodic table, so chlorine has a 1 minus charge. There are 2 of them, giving us 2 minus, but this compound has to be overall neutral, so copper has to have a 2 plus charge. In HNO3, we assign hydrogen as 1 plus, and then we assign oxygen as 2 minus. We have a 1 plus, and then we have 3 oxygens that are 2 minus, so 6 minus and 1 plus gives us 5 minus. It has to be overall neutral because there's no charge for HNO3. So that means that nitrogen has to be a 5 plus. And then in ClO3 1 minus, the total has to be 1 minus. We assign oxygen as -2. There's 3 oxygens, so -6. In order for it to equal or sum up to -1, then that chlorine has to be a +5. If we go back to our questions, going back to question 3, we already said that this was an oxidation reaction because it shows us the electrons are being lost. And so that fits our definition that losing electrons is oxidation. But we can also prove it using oxidation numbers or oxidation states. So if we go look at this reaction and we assign oxidation numbers for the iron solid and then the iron 2 plus, we can see that its oxidation number will change, meaning that electrons were transferred. Iron solid has an oxidation number of 0, and then iron 2 plus tells us it's 2 plus. If iron goes from 0 to 2 plus, then that means that it lost 2 electrons. Remember, the charge is going to increase because electrons are negative. So if you lose negatives, lose those electrons, the charge increases. Gaining electrons, we're going to see a decrease in those oxidation numbers going from reactant to product. Okay, we're going to do the same thing for question 4. 4 electrons plus O2 plus 2H2O yields 4 OH minus. This is showing reduction because it's showing electrons are on the reactant side and they are being gained. We can do the same thing where we assign oxidation numbers on this one. O2, that oxygen has an oxidation state of 0. In water, the hydrogen's a 1 plus and the oxygen's a 2 minus. And then on the product side, in OH1 minus, hydrogen's a 1 plus, oxygen's a 2 minus. And so we see the oxygen in O2 was an oxidation number of 0, but on the product side, it's an oxidation number of 2 minus. So that tells us that those oxygen atoms gained 2 electrons. Again, fitting our definition for reduction. Thinking about the equations we just looked at, what is the difference between solid iron and iron 3 plus at the atomic level? So when we talk about at the atomic level, we're talking about the subatomic particles. What is inside those atoms? And so when we talk about subatomic particles, we're talking about protons, neutrons, and electrons. Iron solid and iron 3 plus are both iron. So by definition, they're going to have the same number of protons because protons determine the atom's identity. But they're going to be different in terms of their electrons because they have different charges. Iron solid is going to have 3 more electrons. Iron 3 plus has lost 3 electrons. So same number of protons because they're both iron, but a different number of electrons. Question 6, in the article, the equation Fe2 plus 2OH minus yields FeOH2 solid is shown as an intermediate step in the formation of rust. Does this represent oxidation reduction? And if not, what type of reaction does it represent? So again, to identify if we're looking at oxidation reduction, you have to assign oxidation numbers. Figure out what are the charges or the oxidation numbers for each of those elements, and do they change going from reactant to product side of this equation. Iron 2 plus, that iron has a 2 plus charge. In OH1 minus, our hydrogen's a 1 plus, oxygen's a 2 minus. And then in FeOH2 solid, oxygen or hydrogen's a 1 plus, oxygen's a 2 minus, and iron's a 2 plus. Nothing changed. Everything had the same oxidation states going from reactants to products. So this is not a redox reaction. Instead, we would identify this as being a precipitation reaction. It's got 2 ions forming a solid precipitate. This would be like our net ionic equation for a precipitation reaction, which is what we've been looking at in goal 4.1. Okay, question 7. How does the equation for iron hydroxide solid plus O2 gas yields 2 Fe2O3 plus 4 liquid water in the article illustrates oxidation of iron? So again, I identify oxidation numbers, see if oxidation numbers change to say if something's being oxidized or reduced, and if this is a reduction, as if this is an oxidation reduction reaction. In FeOH2, iron's 2 plus, oxygen's a 2 minus, hydrogen's a 1 plus. In O2, that oxygen has an oxidation state of 0. In Fe2O3, that iron's a 3 plus, oxygen's a 2 minus. And in water, oxygen's a 2 minus, while the hydrogens are 1 plus. We see oxygens and irons change oxidation numbers in this reaction. So this is a redox reaction. But not only is it a redox reaction, but we can further identify what is being oxidized and what is being reduced. Our oxygen goes from 0 to 2 minus, meaning it gained electrons. So oxygen in O2 is being reduced. The iron in FeOH2 goes from a 2 plus to a 3 plus charge, so it loses an electron. That iron is being oxidized. Okay, if you wanted to make something out of metal but prevent it from rusting, what are some of your options? And again, this question came straight out of our article. Using less reactive metal or coating the metal with paint to prevent it from making direct contact with water. Because again, we need water to facilitate that transfer of electrons. And result in that formation of rust.